Now we're going to look at our next major topic, and that is how do we prove things, right? So one of the things to keep in mind is that as humans, the way we learn things is often through experience. And so we may take our experiences and generalize from that. And when we do that, we're performing what's called inductive reasoning. So an example might be that most of the people that I've met are right-handed, so I conclude that among the general population, most people are right-handed. I haven't met all 7 billion people on the planet, but based upon my experiences with a very small subset of those people, I conclude that most people are right-handed. Deductive reasoning, though, begins with a set of hypotheses and some set of rules, and those together can be used to reach conclusions. So when we were using modus ponens, when we were working with logic, that was a form of deductive reasoning. That is, given P, that's some hypothesis or premise, and knowing that P implies Q, we can conclude that Q is true. Okay? So how do we go about proving things? There's a number of ways to prove things, but the ones we'll look at will be direct proofs, proof by contraposition, proof by contradiction, these are not the same thing, and mathematical induction. Now, one of the mistakes that people often make is to think that if they tried something with several different numbers and it always worked, then they've proven it to be true. That's just not the case. That may make you believe something to be true, and you may be right, but it's not actually a proof, not in any mathematical sense. However, it only takes one counterexample to disprove something. So even if something is true for an infinite number of things, but there's one thing for which it's not true, well, then you can't say it's always true. So we'll look at direct proofs first. When we were proving conjectures using propositional or predicate logic, we were creating direct proofs. And if you recall, these often took the form of A led to B, B led to C, and so forth. That is, they were in the form of implications, right? We had a set of hypotheses, and we knew some relationships, and we used those to move from one thing to the next, to the next, to the next. So we went directly to the last thing, a step at a time. And that's why they're called direct proofs. Okay? So let's look at some examples of direct proofs. Now, one of the things you have to keep in mind is that in order to prove things, you typically have to have some type of domain knowledge. What does that mean? Well, if I want to prove things about physics, I typically need to know something about physics. If I want to prove something about statistics, I typically have to know something about statistics. Those are the domains involved. So what is it that most people know if they're taking a discrete structures course? Well, most courses that teach how to solve proofs, at least introductory versions, do something from what's called number theory. And even though it's unlikely you've had a course on number theory, that's something you could take in a math department. But number theory is the study of integers. And the reason why this is useful as a way to prove things is because you already have some experience with integers, right? You've heard of even numbers, even though you may not know the formal definition. You've heard of odd numbers. You do know both of these are integers. So what is the actual formal definition of an even integer or an even number? Okay, so we would say that m is an even integer if it's equal to 2 times p, where p is any integer. So what do I mean by that? Well, we're not restricted to p being even itself or odd or positive or negative or zero. It can be any integer. But if we can write m as 2 times some integer, then we would call that even. So we'll have a couple of examples. Let's do this. Let's do p. We'll have m. So let's say p was negative 1. Well, it's 2 times negative 1, which is minus 2. That's considered even. 0. 2 times 0 is equal to 0. 0 is considered even. 1. 2 times 1 is 2. Surely you know that's even. 10. 2 times 10 is 20. That's even, and so forth. An integer is odd if it can be written as 2 times q plus 1, where q is any integer. All right, so n is an odd integer if it can be written this way. Let's do this now. So once again, we'll do something like this. Minus 1. 2 times minus 1 plus 1 is what? Well, that's minus 2 plus 1 is negative 1. 0. 2 times 0 plus 1 is just 1. Positive 1. 2 times 1 is 2 plus 1 is 3. And we can see if we keep doing this, we're jumping 2 at a time. Just like this was a difference of 2. Of course, this wasn't, but had I went to 2, 3, 4 for p, we would have been making jumps of 2. And we're doing the same thing here. It's just a different set, right? So if we were looking on the number line, right? So even, 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 and so forth. We also need to know a couple things that come from the axioms for integers. Axioms are the foundation of mathematics. And what axioms are things that we assume are true because they seem so obvious. For example, we know, we're going to use these here, we know that if I have two integers a and b, so a and b are both elements of the integers, we know that a plus b is equal to b plus a, right? 3 plus 4 is equal to 4 plus 3. This is what we call commutativity. And we also have associativity and the distributive property and things like that, okay? So what we also need to know is that, once again, if a and b are integers, then a plus b will also be an integer, and then a times b will be an element of the integers. Adding two integers gives us another integer. Multiplying two integers gives us an integer. Okay? So these would be useful things to know in terms of doing our proofs. So what might we prove? Well, let's say, for example, I was looking at this and I said, okay, 4 plus 3 equals 7. You're probably thinking, oh yeah, that's obvious, that's nothing. But I look at this and realize I'm adding an even number to an odd number, and I got an odd number. So the question is this always true? That is it always true that the sum of an even number and an odd number, which are integers, will produce an odd number? Okay? Now, going back to what I said earlier about counterexamples, if somehow you were to find that 100, which is even, plus 99, which is odd, produced 200, which is even, then you would know this is not an absolutely always true statement. Okay? But obviously this isn't really true. In fact, it is a true statement. So how would I prove that? Now, if we had a small set of numbers, if I said, okay, is it true that, the even integers from the set, 0 to ... 9 or 8, actually be the last one. You could say the even integers from the set, and I could actually write all the integers. Okay? Or the odd integers, 1, 2, or excuse me, 3, 5, ... 9. Well, then I could actually just try every combination of these and work it out. But if we're talking about all integers that are either even or odd, we're talking about an infinite number. So there's no way I can go through and prove it for all those. And even if there's a finite number like there is here, it may be more numbers than I want to work with. So we need some way to do this in the general sense. So that's where we're going to go back to our definitions. So remember, we said an even number, m, M is an integer that's considered even if it can be written as 2 times P, where P is an integer. And N is an odd integer if it can be written as 2 times Q plus 1, where Q is an element of the integers. So this is the way of generalizing to any even integer and any odd integer. So let's see what happens when we do this right here. So even plus odd would be M plus N, which is equal to 2 times P plus, and we'll put in parentheses to make sure we realize this is the odd number, is this right here, which is equal to just 2P plus 2Q plus 1. I'm using the associative property. And what do these have in common? Well, they're both multiples of 2. So I can factor out the 2 and get P plus Q plus 1. Now remember earlier we said that an integer plus an integer is an integer. And so what do I have here? 2 times any integer plus 1 is what I get when I add M to N. That's an odd integer. So this is my direct proof that this statement is always true. I didn't plug in real numbers like 4 plus 3 other than to try to understand it. And personally, when I'm trying to convince myself of something being true, I may do something like this to better understand it. I may say, wow, let's work through a few examples, just like I did with you here. Does this prove it's true for every single value of P or Q? Well, no. This is just to sort of convince you that it's true, but ultimately we're relying upon these definitions, and that's what they are, definitions. Okay, so I didn't prove that even numbers are always this. That's the definition of it. And I didn't prove that this is always an odd number. This is the definition. And these axioms are what we relied upon too. But hopefully you can look at this pattern and realize, oh, yeah, this does seem to be what an even number is and what an odd number is, if you didn't already know that. Okay? So I'll make another video to do some more examples of direct proofs.